Now let's try to see few very special examples of separable differential equation. As you know, we have this general method that we can use to solve separable DE, where we need to separate the variables by the means of equality, and once that separation is done, you can integrate both sides using various integration techniques to get the general solution. If initial condition is given, one can calculate a particular solution. Now just think about it, how many different type of problems that one can construct using this idea. For example, I can create example that uses direct matching on variable y side, direct matching on variable x side. Or you can produce an example where you have direct matching on one side, u substitution on the other side, u substitution on both side, or integration by parts on one side, spatial substitution on the other side. Lot of different and interesting type of problems can be constructed using this interesting ideas. Let's try to start this solution technique with something reasonably simple. Let's say I would like to find out the general solution. Find the general solution of this differential equation, dy by dx equal to, let's say I have 4x cubed plus 6x square plus 7. Alright, we already know that this is a separable differential equation. Right side can be seen as a function of x multiplied by constant function of y. Okay, our first goal is to separate the variable by the means of equality. So I want variable x on one side, variable y on the other side. Clearly I wanted to turn this differential equation into differential relationship. Alright, I get 4x cubed plus 6x squared plus 7 times dx. Be sure that dx and dy stays in the numerator, otherwise we will have a hard time integrating function. Alright, once the variables are separated by equality, we would like to integrate both sides. Very carefully select the technique that you are going to use to integrate both sides. Seems like the left side requires me to use direct matching with the formula. We know how to integrate one with respect to y. The right side is a polynomial in variable x. Direct matching, power rule in fact for integration, and constant rule for integration is needed to integrate the left side. If simple integration technique like direct matching or algebraic simplification is needed, you can apply these techniques on both sides simultaneously to get the general solution. Alright, antiderivative of 1 with respect to y is y. Antiderivative of 4x cubed is 4x to the 3 x to the 4 over 4. Antiderivative of 6x squared is 6x cubed over 3. Antiderivative of 7 is 7x, and as I said, throw a constant of integration on one side to get the general solution. If there is a cancellation between numbers in any term, you would like to perform it. In other words, try to write each term in its simplest possible form. What you get is called the general solution of the given differential equation. Right? So it's that simple. Alright, if you feel comfortable with basic integration technique, then this type of problems, they are piece of cake. Alright, you just separate the variables and integrate left side with respect to y, right side with respect to x, and then you get your general solution by setting this to antiderivative equal to each other and throwing constant of integration on one side. Okay, here is one more problem very similar to first one, but let's say want you to solve initial value problem. Find the particular solution of IVP given by dy by dx equal to, let's say, 3 over 4y plus 5 whenever x value is, let's say, -2, corresponding y value is 1. Alright, again I want you to see this initial data in form of y at x naught equal to y naught. This bracket inside quantity refers to the x value, the right side quantity refers to the corresponding y value. Let's separate the variable, get the differential relationship, multiply both sides by 4y plus 5, and then send this dx over to the other side, and then integrate both sides with respective variables. Direct matching is a technique to use here. Let's get the entire derivative. Entire derivative of this side is going to be 4y square over 2 plus 5y. Entire derivative of the right side, it's gonna be 3x, and then I'm throwing constant of integration. Let's simplify these numbers in the first term. I get 2y square plus 5y equal to 3x plus c. Remember, the general solution is an infinite family of solution. Every different c value gives you one new solution. Out of this infinitely many solution, I would like to pick the unique solution that goes through the data point -2, 1. Alright? So what I want you to do is substitute x equal to -2 and y equal to 1 in here and solve for c. Alright, there are only 3 unknowns. I am supplying you values of 2. Easy to compute. The third variable, third unknown, 2 times 1 square, 5 times 1 equal to 3 times -2 plus c. Seems like this is 7 equal to -6 plus c. C must be 7 plus 6, which is 13. Alright. Throw this particular c value into your general solution and write down the particular solution. Alright, so our particular solution is going to be 2y square plus 5y equal to 3x plus 13. Alright. Okay, so these are ideal type of problem to start our discussion with, where I use direct matching on both sides. Let's make this discussion slightly more interesting. Let's construct an example where more interesting integration techniques are needed. Let's say find the general solution of this differential equation dy by dx equal to, let's say I have 2x square plus 3 times e to the y square minus 1 divided by 2xy. Alright, looks like this is a function where variable x can be seen separately from variable y. It's clearly a separable differential equation. Variables can be separated without any difficulty. Alright, so I want function of y on the side of dy, I want dx on the side of function of x. In other words, I would like to get the differential relationship from this differential equation. Be sure dx and dy should stay in the numerator, because if that's not happening, then that means you will have a hard time getting rid of them. Alright, so we are going to integrate both sides, so that's why we need dx and dy in the numerator. Alright, so let's move this function of y on the side of dy. Multiply both sides by y. Divide both sides by e to the y square minus 1. That will bring that expression involving y onto the side of dy. And then dx is already in the denominator. When you move it onto the other side, it will be going into the numerator. All you have to do is integrate both sides with respective variables. Think about it, what integration techniques are you going to use to integrate both sides? Alright, looks like here I have multiple terms in the numerator with a single term sitting in the denominator. Algebraic simplification is a technique to use. Alright, on this side I have y divided by e to the y square minus 1. Alright, remember there is no quotient rule in integration theory. So what I want you to do is first try to use algebra to make it look simple, meaning send this denominator into the numerator, right, by reversing the sign of that exponent. So I get y times e to the negative y square plus 1 dy equal to, if I use algebra on this side, I get x plus 3 over 2x. Alright, looks like algebraic simplification is performed here. I can integrate this thing right away, direct matching with the formula. Try to find out which integration technique you are going to use here. Alright, this is a product of two different type of function, so I have to choose between use substitution and integration by parts. Again, let's make it simple. Focus on the inner layer of the composite function. Seems like the derivative, variable part of the derivative of the inner layer is going to be y. Seems like that variable part is multiplied with this composite function. It's a standard u substitution problem. Alright, so u sub is needed on this side. When you need more complicated integration technique to be applied, then I recommend you guys to do the computation of antiderivative on a side. This will make the process very fast. Okay, believe me, do not try to handle two complicated integration processes simultaneously, one side with respect to y and the other side in variable x. This will unnecessarily take a long time to write the complete solution. So to make it faster, take that function, take that integral on a side. Let's say I work with this y e to the negative y square plus 1 dy on a side. Start with u being negative y square plus 1. Find the replacement of dy in terms of du, which is negative 1 over 2y du. Alright, make these two changes in your problem, and expectation is it will convert our function in the form of a basic integration formula. Alright, as expected, variable y is gone. We get something that's matching with the formula. Integrate it. Antiderivative of e to the u is just e to the u. Plug the value of u back. I just need one antiderivative. Alright, this is the antiderivative of the left side. I can calculate antiderivative of the right side as well, meaning I am ready to write down the general solution. Let's write it down. Antiderivative of this side is negative half e to the negative y square plus 1. On the other side I have x square by 2 plus 3 half natural log of absolute value of x plus c. Alright, and this is the general solution of the given differential equation. Now let's end this story with one more example that uses the remaining two integration techniques. Alright, spatial substitution and integration by parts. Okay, so here is one problem. Again, convince yourself that in the previous example, if I have given you initial data, then it is very simple to compute the value of c. For example, if I give you initial data when x is 1, corresponding y value is, let's say, 1, right? You can calculate a particular value of c based on the given initial data. That is just a fair computation, so don't really want to spend too much time on it. Instead, let me finish this video with this final example. Find the general solution of this differential equation. Let's say I have y square dy by dx equal to x divided by x e to the y plus 2e to the y. Alright, doesn't look like it's a separable differential equation until you factor out e to the y from the denominator of the right side. Let's do that. Get y square dy by dx equal to x over x plus 2 times e to the y. Okay, alright, it's a separable differential equation. Now I can separate the variables out. Look, I get y square e to the y dy equal to x over x plus 2 dx. Okay, variables are separated by the equality. All I have to do is integrate left side with respect to y, right side with respect to x. Think about it, what integration technique are you going to use? Okay, looks like this is a product of two different type of function. Composite function is missing, meaning integration by parts is the only option that we have here. Alright, direct matching fails. Algebraic simplification not really possible because there are two terms in the denominator. U substitution, it's not gonna work. It's not integration by parts as well, so spatial substitution is what I would like to try in here. So spatial sub and integration by parts. As I said earlier, do not attempt to do these two different techniques simultaneously. Instead, do these two techniques on a side, one by one. Okay, keep that solution on the same page. Let's say I would like to work with the left side first. I have integral of y square e to the y dy. Okay, I'm gonna use that tabular method, compare it with the left side of the formula, integral u dv, make a selection of u according to that LAE rule. Alright, obviously this is a product of algebraic and exponential function. Algebraic function should get priority to be the value of u. So let's create this table. Where the first column stores the value of u, the second column stores the value of dv. My u is y square, dv is e to the y. As you know, I'm gonna differentiate u, I'll integrate v. If choice of u is algebraic function, go ahead, differentiate it. Derivative of 2y is 2, derivative of 2 is 0. And then I get e to the y here. So get y square e to the y, 2y minus 2y e to the y plus 2 e to the y plus 0. So this is the entire derivative of the left side. Let's calculate the entire derivative of the right side. Likewise, I need to use spatial substitution here. X over x plus 2 dx. Start with u equal to x plus 2. Du is dx, meaning replacement of dx is du. We make these changes in the problem. This is what we get. As you know, this is an issue that variable x did not disappear. This was the reason why we call it spatial substitution. Go back to your substitution variable, solve it in form of x as a function of u, and then plug that value back in here. So as you know, what u substitution does is, what spatial substitution does is, it will allow you to convert your ratio in such a form where algebraic simplification works fine. Seems like we get 1 minus 2 over u du. Fairly easy to integrate it. U minus 2 log absolute u. I'm gonna plug value of u back in there. I get x plus 2 minus 2 natural log of absolute x plus 2. Alright, so we have antiderivative of the left side, antiderivative of the right side. All we have to do is set them equal to each other, and then throw a constant of integration on one side to make it a full family of antiderivative. Now if it's clear in your mind that 2 is a constant too, c is a constant as well, if you add 2 and c and just write c, that will be fine too. Alright, so let's call this a general solution, or as I said, you can combine that 2 with c and make it look like this. Okay, alright, so that's a full solution. Again, if you have any difficulty with any of this material, feel free to shoot me an email. I'll be more than happy to clarify these things out for you. Thank you.